This video covers trigonometric graphs. We're going to base a lot of our construction of these graphs on our knowledge of the unit circle. We're plotting on this circle the points that are found on the unit circle at our main increments of 30 degrees, 45 degrees, 60 degrees, and then the points that are on the x-axis and the y-axis. Now the equation for this unit circle is x squared plus y squared equals 1. That comes from a standard equation of a circle where the center is at the origin at 0, 0, and the radius equals 1. Let's go through and identify the x and y coordinates of each of these points. First here, definitely we're at 1, 0. Next, at 30 degrees, what I think about to remember all these ordered pairs is basically two main triangles, a 30, 60, 90 triangle, which I've drawn in here, and I know the lengths of these sides. The long side is radical 3 over 2, the short side is 1 over 2. I just have to have this triangle memorized, but this horizontal side is the x-coordinate, and the vertical side is the y-coordinate, so I know the ordered pair here is radical 3 over 2 and 1/2. The next angle measure at 45 degrees represents the other triangle I have to remember, a 45, 45, 90 triangle, and since these angles are equal, these two sides are equal. The x and the y coordinates are equal, and they are both radical 2 over 2. So the fractions I have to remember aren't too difficult either. It's a radical 1 over 2, which we can simplify to just be 1 over 2, a radical 2 over 2, or a radical 3 over 2. And if you wanted to get fancy, you could say that this 1 right here is a radical 4 over 2, which simplifies to 2 over 2, which is 1. If it helps you remember these ordered pairs, then go for it. Next measure at 60 degrees, it's again just the 30, 60, 90 triangle, but flipped over. So now my x-coordinate is the short side, the 1/2, and the y-coordinate is the long side, the radical 3 over 2. And back to this point now, our x-coordinate is 0, y-coordinate is 1. Now that we have these ordered pairs filled in, all the other ones are simply reflections of these points. So if I'm thinking about the next point here at 120 degrees, it's a reflection about the y-axis from this point here. If it's reflecting about the y or symmetric about the y, it means they'll have the same y value. So it will have another ordered pair with radical 3 over 2 for the y-coordinate, but the x value has its sign flipped from positive 1/2 to negative 1/2. So the rest of these points are all reflections. If I'm thinking down here in quadrant 3, like this point right here, it's in the middle on one of these diagonals, a 45, a 135, 225 down here, but that's a reflection. So the x and y are radical 2 over 2, but have been reflected over x and y, so negative radical 2 over 2, x and negative radical 2 over 2, y. How about this point down here, quadrant 4? Either we're thinking reflections, or even I'm still thinking at this point about which of these triangles fits in. It's definitely a 30, 60, 90 triangle. My short side is horizontal, my long side is vertical. That helps me remember that the x-coordinate is the horizontal, so the x-coordinate is 1/2. The long side is vertical, so it's a radical 3 over 2, but since we're going down into quadrant 4, that must be a negative y-coordinate, a negative vertical distance. Now again, the graph we have here is simply the graph of a circle with radius 1, x squared plus y squared equals 1. Even though we know that in these ordered pairs, the x-coordinate is equal to cosine of the related angle, so this ordered pair would be cosine 30 degrees and sine 30 degrees, and that's the case for all of these ordered pairs. I could tell you from this point down here, which was 300 degrees, that cosine of 300 degrees is 1/2, sine of 300 degrees is negative radical 3 over 2. So we're using trig functions in here to see how these values work, but it's not really a graph of cosine or sine yet. To make that graph, we are going to use for our independent variable the angle. So we'll be marching along the circle, but our x-coordinate is going to now be the angle that we've rotated. And our y-coordinate, the dependent variable, will be cosine of that angle. We're still going to remember all of those ordered pairs as we fill in our table. At 0 degrees, what is cosine? So I'm thinking cosine is the horizontal coordinate. At this point right here, which is at 0 degrees, our x value is 1. And we'll just march along. So at 30 degrees, our x coordinate is the long side, which is radical 3 over 2. Since I'm going to make a graph, we're using some decimal approximations. It's rare that I like to go with decimal approximations, and I'll keep reminding you of what the exact values are, but for this table, we're going with decimal approximations. And in fact, it is helpful to recognize some of these decimals. So this 0.87 I've rounded from a decimal number that starts with 0.866. So if you see that, it often is a result of a radical 3 over 2. Let's keep going around the circle. Next is radical 2 over 2. As a decimal approximation, it's 0.707. That's how I recognize those digits, and I rounded it further to 0.71. Next, 60 degrees, and now our horizontal is the short side of a 30, 60, 90. That's 1/2. And up here to 90 degrees, now our x-coordinate up there is 0. Okay, let's keep going along. Next is 120 degrees. Horizontally, I have to go back by negative 1/2. At 135 degrees, I'm going back negative 0.71, the radical 2 over 2. And at 150 degrees, I'm using the long side of that triangle, radical 3 over 2, negative, since I'm going to the left, the negative 0.87. And now at 180 degrees, x-coordinate is negative 1. Now you can see the repeating pattern of these values. We'll continue horizontally. This is negative radical 3 over 2, negative radical 2 over 2, negative 1/2, then 0. Now we're going to be using positive x values again, so at 300 degrees we're back to a positive 1/2. I don't have room here, but we know what these values are. At 315 we'll be at a positive radical 2 over 2, and then a positive radical 3 over 2, and then back to positive 1. What's important for us to know is that we could keep using increasing values for theta. I could have another point where theta equals 390 degrees, and then 405 degrees, and 420, and so on. So this graph doesn't stop after we've gone all the way around the circle, but a pattern that repeats has finished. But that pattern will continue to repeat for additional rotations around the circle. Let's start to plot these points. I'm choosing to use this graph here, which can handle y values between negative 1 and positive 1, and I say y values meaning the cosine theta, and our x values, the horizontal, is our theta measure. We're actually plotting theta and cosine theta, and each of these increments represents 15 degrees. I have to be aware that even though these are our main angle measures, they're not evenly spaced. They're 15 degrees apart here in the middle, but 30 degrees apart from these points that are on the x-axis and y-axis. So 15-degree increments will allow me to handle each of these numbers here. Okay, 0, 1, then at 30 degrees, so I've jumped 2, 15, 15, then 30 degrees, and I'm going up to the radical 3 over 2, approximately 0.87. And we'll continue to plot these points here, where our theta is horizontal and our cosine theta is vertical. Here we are at 180 degrees, and we've gone down to negative 1. At 210, we see our cosine values increasing again. Here's 270. There at 300 degrees, we're at 0.5. That's where our table ends, but we know those other values. We could fill those in. And that is one full rotation. We're back to 360 degrees, and cosine of 360 equals the same as cosine 0. It equals 1. But we do know that theta can continue to increase, and we'll get these repeating cosine values. So I'll fill in those dots there. And it can even go in the negative direction. We know negative rotations will go clockwise on this circle. So a rotation of negative 30 degrees will have the same value as 330 degrees. I'll try to connect all these points with a smooth line, but little short strokes is the key for me to trying to come up with a decent looking graph. And this is enough of a graph for me for now, because I'm able to see an entire repeating pattern. I don't need to see too much more than this. I understand that this pattern will repeat over and over and over again. So let's go ahead and construct the graph for sine theta.